Hello everybody, welcome back to another lecture on operating system. Let's start with the operating system structures in this video. So in this we are going to discuss about different structures of the operating system, which basically is concerned about how the components are connected to each other. So the number one is the simple and monolithic structure. In simple and monolithic structure, as we see that there is no well-defined structure because it's small, limited, and simple structure. Simple is either like monolithic, both are related, and the interfaces and the functionality levels are not separated. For example, if we are working in the user module, it have the access to all the resources. So there is no separation of the functionality and the interfaces. Example is MS disk operating system, and because if one program fails, the entire system is crashed because it have the direct access to the resources. What are the advantages? As it has the direct resource, so it is easy to develop, and because they due to the direct access we don't need so many interfaces, so it's a better application performance with a few interface. But the only disadvantage is that there is no data hiding, because if every application can access the resources, it means there is no data that is hidden, so security is less. So similarly, there are no boundaries in the modules. Everyone has the similar action, everyone can do the same thing, so there is no boundary in the module. Now the second one is a microkernel. Microkernel means small. Micro means small, so kernel is small. All the unnecessary applications are removed from the kernel and are added to the user space. They added to the user space. So here user space is large and the kernel area is small. Kernel area means which have the access to the hardware, that is small. So as a result, we have the smaller kernel. Advantages are so many things are added to the user space. So kernel doesn't have to be modified. So if we are going to add something into our hardware or into our program, into our computer, it could be added directly to the user space instead of adding it to the kernel. As we know that adding into the kernel requires a lot of modifications and changes, so it's a better option. But the disadvantage is that now we are adding everything to the user space, so the module communication is increased. So because we have so many modules, if one have to communicate with the other, it have to involve the kernel at first, and then kernel will switch to that mode, again to that mode, so it will have the inter modular communication, and that would increase the overhead and decrease the performance. So this is not ideal sort of kernel or structure of an operating system. The third is a hybrid kernel. Hybrid kernel is a mixture of monolithic and microkernel. So we get the speed and design of the monolithic kernel because everything have the direct access to the resources, and stability from the microkernel. And what are the advantages? It may have various sort of hardwares. There is a security. There is a stability, and so that's why there is a reliability. But the only disadvantage is that it is complex because it is hybrid. So it is complex and it reduces the performance because these two have different workings and ultimately the performance is reduced. And number four is the exokernel. So it provides the application level management of hardware. So application level of management is provided by the exokernel. So it provides resource management, resource protection. It is small in size, which is a plus point, and it have limit abstraction use, and there is also a freedom. What are the advantages? The performance is higher and hardware resources are used efficiently. The disadvantage is that it consistency and it is complex. So there's a problem in consistency and the complex structure of this. The next type is the layered structure. This is, so we have the operating system divided into layers. We have the entire system divided into layers. There is layer 1, which is a hardware layer, and there is a layer, and in the top one is the interface or the user layer, interface layer. So it is designed in such a way that the upper layer have to be dependent on the lower layer. So the top layer uses the function of the lower layer. So the bottom layer is a hardware layer and the topmost layer is the user interface layer. The advantage is that debugging. The debugging is easier because the above layer is always dependent on the lower layer, so we can easily find the errors. We can trace the errors. And then data modification at each layer. Every layer is marked by data modification and it is passed to the next layer, and it is used in the Unix operating system. Then the sixth one, we have the modular structure. Modular structure is considered to be the best approach to now. Modular means we are adding the modules. Modular depends independence. So it depicts the independence. So different modules have to be independent. So we are only having the core components initially, which is the kernel. So at the, for example, at the runtime we have the kernel. At the booting time we are assigning different layers. We are having the modular structure, we are adding more components. So it is more flexible than layered, because any module can call the another module. It doesn't matter that only it is dependent on the lower module or lower layer. It can call any other module, and it is used in Solaris operating system. The seventh type is a virtual machine. Virtual machine is like a host. We have a guest operating system onto our host operating system. So we can have the virtual machine if we want different operating system to run on the our computer and the devices. So here is a VMware, and it will have the access to the hardware along with the CPU, disk drive, RAM, which is of your computer, and it will allot it to different executions. So it can have different processes running on it. So it gives the impression as the execution environment is a different computer. So it's a virtual box, and it can run the multiple processes, and it pretend the use of the processors. So it also involves the CPU scheduling and the virtual memory. The only disadvantage is that as we have the disk systems, so if host needs 6 systems and VMware need the disk space, but the disk space couldn't be available to all the devices, so virtual disk have to be used ultimately. So clear. Afterwards we have the modes. So we have different modes. There's a user mode, there is a kernel mode. The one which we are working, like, which is non-privileged mode, that is the user mode. It is the restricted mode, it have limited functionalities. So after booting directly, the user module is launched, it is less privileged, and it cannot access the resources directly. In order to access the resources, it have to make a system call to the kernel, which in charge will have the uh, access to the resources, and it is depicted by the mode bit, which is always 1 for the user mode. Similarly, for the kernel is master or the privileged mode or the super mode. Okay, kernel have the access to all the hardware devices, including the memory, disk space, etc. So it's a most privileged program of the system, and if it is interrupted, the whole system can get down, because it has the direct link to the resources. If any of the resources have some sort of like disruptioning or interruption, the whole system is down. And all the processes, they share the single virtual address, and it's depicted by the mode bit, which is 0. And now we are starting with very important topic, which is of the system calls. System call is like, it is a way, it is a technique in which a computer program would request a service to the kernel, which will have the access to the hardware resources. So this request have to be to access these resources, and it have to be made by the computer program to the kernel, because this is in charge of the hardware resources and other devices. So it is a way to interact with the operating system. So what happens when we are making the system call? It is interacting with the OS, it is asking for the service, and it's providing to the user. And this all occurs with this interface, which is the application program interface. So entry point of the kernel system. It's the entry point of the kernel system. And then we have system call. It could be written in high level language, or it could be written in assembly language. High level like C language, Pascal. So here we can directly invoke the system calls by the predefined function. For example, we have fork if one process creates another process. We have exit. So we have so many system calls. If we need to read from a file, so we can have the system call of read, write system call. So there are so many system calls. And then example, if I am running a program in that I am having any system call, so it would request for the service to the operating system. And operating system will allow switching the kernel. Operating system will allow switching the kernel. It will give the control to the kernel, and then it would handle the request and perform the operation, return back to the program it was called by. And then this system call also helps in ensuring the proper functioning of operating system, because normally we are in user mode. After the booting process, the initialization is done in the user mode. So in order to access any of the resources, it have to make a call to kernel, and this call is the system call, and this kernel will respond or give them back the hardware and respond to the call. Then we have the services of the system call. It helps in process creation. We can create new processes, we can manage the memory, we can have the access to the files, directories, manage the file system, we can handle the device system. There could be protection and there could be networking. Now we have the features of the system call. Number one, it provides the interface between the program and the kernel. Because in order to access the resources or the services of the operating system, program have to interact or make a system call, and system call will ask from the operating system about the services, and kernel will take the hold and would return with the answer. Number two is protection. So because the user mode have to make the system call in order to approach the kernel, so it's the kernel who have the access, not the user. So it can give us the access of all the devices or all the resources that are privileged. That is, a privileged operations can be achieved with the help of system call. Number three is kernel. So kernel have the access to the entire system, including the hardware and the memory. So we can also have that access. Then we have the context switching. It is ideal in CPU scheduling. For example, if we have to change from one process to the other process. For example, this process is of higher priority and we were already running this process. So it's a duty to shift this process into the ready queue and make it run earlier than this. So that happens with the CPU scheduling, and it is possible if we have the CPU scheduling. So context switching is only possible if we have the preemptive scheduling. And then we have the error handling. For example, when making a system call, it can give us all the error code, it can return with the error code, so that we can check about the error in the program. And then we have the synchronization is to it is used for the resource safety. For example, it provides the logs so that at one time or at any time we can access to the proper resources, and in the in the proper format. It should not be wrong either. And what are the advantages? That's already covered. We have the access to the hardware, we can use the memory management, we have the process management, we can use the security and standardization. Standardization means it provides a standard way of working, because the user have to access the kernel mode, user mode have to enter into the kernel mode in order to access the resources, standard resources of the computer. And now let's discuss about how does it work, how the system call works. It it could be divided into the five processes. I've listed it down this way. So number one is that user needs the hardware. When user needs the hardware, so we are running a program and the user might need the hardware. For example, we need a file to read the data, so that program would make a system call, and the operating system will listen the system call or will see the system call and give the control to the kernel, so which is a privileged mode. And then operating system is going to solve the operation or perform the operation. For example, we want the file to read, so it would read the file, and then operating system would go give the control back to the user program, and the execution could be completed. So this was how the system call works. The next one we start with is the process management. It is very, very important concept of operating system. So what's the process? It's a program under the execution. So there could be multiple processes in the computer. So a program under execution is known as a process. So what's the duty of the process management? It would schedule the processes, track them, and then dispatch them. And the user can get the full control of the CPU. User should think as if it gets the full control of the CPU. So what does process management actually means? It's are the techniques used by an organization to design, monitor, and control the processes and make them run in an effective and efficient manner. And here we can use so many system calls that were earlier discussed. So we can use create, terminate, wait, block, and ready, etc. And then we have the memory management, how the memory is managed for these things. So we have stack memory, heap memory, data, and text. So in the text, the program instructions are stored, the program counter is stored, so that while reloading the process we can have the access to that program. In the data, we store the global variables. In heap is always for the dynamic allocation of the memory, and the stacks is all with like temporary data and the local variables. So stack will store all the temporary data. And now if we classify the process management into the components, so first we have the process mapping. Mapping is always done with a visual representation. It can make the diagrams to discuss about how the job is flowing or how the task is flowing, which task is dependent on the other task. And then we have the analysis for good or bad things. We can have the area of improvements, we can identify the bottlenecks. And then process redesign means we can create the new process, we can make the changes to the process. Then process implementation, so those redesign processes we can introduce into the organization, so we can have the execution of those processes. And then we have the process monitor control, and we can control all the key points for the better execution of the process. And now, the most important topic for the process management is a process control board, which is a PCB. It's a process control board. It's a unit of the process control management. So, it is the task controlling the block. So, it's the task controlling the block. It's the data structures in the operating system with the help of the kernel. It's present in the kernel. So, it have the information to manage the processes. Or we can say that it is a manifestation of the process in the operating system. So it helps us with the errors, data loss, time cut down. These were all the points that need to be covered in the monitor control. So one process control board can be linked to another process control board, and each process have the unique PCB. This must be remembered. Every process have their unique PCB, and the units or the components of PCBR versus process ID, and it is provided by the operating system. We can see it in the task manager. Every process have the unique ID. Then we have the process states. This we will discuss whether it's in ready state, running state, waiting state, different stages of the process execution. And then we have the CPU registers, which is a program counter, because for reloading, unloading of the data, we need the program counter to start with the process. And then we have accounts information, which states that how much CPU is used, for how much time it is used, how much time is taken to complete a process. And then we have the input output states. It would tell the devices the process have asked to access, or which files were accessed in the process. And then we have the CPU scheduling, which is the priority, which determines the priority, so which process has a higher priority would be executed first. And these all components are known as the context of the processes. So now we have the process states, which is important. We have the new state. So all the newly created process lies in this state. Ready state, all the processes which are ready, means waiting for the CPU, are in the ready state. Running state, so when they get the CPU, they start executing. That's a running state. Waiting state, if any process needs the hardware, so it would go into the waiting state. And then we have complete or terminating state, where once the process is successfully completed, it goes into the completion state. We have suspended it means that after any error, for example, if the queue is filled, some of the processes are suspended. So if the queue is full, some of the processes are suspended, so they try to cover and occurs in the suspended ready. This is a diagrammatic representation. So we have the job pool, and the processes move to the ready state. Here they wait for the CPU, and then when they get the CPU, they start running and executing and goes to the running state. And afterwards, if they need a hardware, they goes to the waiting state. After waiting state, they couldn't directly access the CPU, they have to wait. Like they have to get ready and they have to wait for the CPU to be allocated to them, and then they would run again. And next we have the context switching. Context switching is that when there is a multi-programming operating system where so many processes are running at the same time, in that time may have different priorities for different process. For example, here P2 may have higher priority than P1. Although P1 was started earlier, so it's the duty of the operating system to save its information into the stack, like where it was left, and it will load the P2 and starts executing. And after this is executed, the P1 will be reloaded from the stack. So this is the concept of context switching, and it is used in CPU scheduling. Then we have, why does context switching occurs? As you already told you, if a higher priority process occurs, or if an interrupt occurs, if we need to switch into user to kernel mode, or in the preemptive scheduling. Preemptive scheduling means where one process could be taken off of the CPU and another process could be run if needed. Okay, so with a shorter burst time could be run executed first. So there are two types of processes. One could be CPU bound, another could be input output bound. CPU bound is one which could lie more in running state, so which needs CPU all the time to make the computations and perform certain calculations. Meanwhile, IO bound are those which are highly dependent on the input output resources. So they would spend more of the time in the waiting queue. So there are some programs which are schedulers, they handle the process scheduling. So they are divided into three types: long term, short term, and middle term. Long term, the work of long term schedulers are to take the process from the job pool and make them into the ready process. So they have to wait for the CPU. So the entire process of taking the process from the memory and putting it into the ready queue is a job of long term processes. We have the short term schedulers, which are also known as dispatchers, and their duty is to provide the CPU to every process, and it's their duty to decide which process should get the CPU. Then we have the middle, which involves the swapping, and they like lesson on the multi-programming systems. And then it's the duty of the schedulers or the long-term schedulers to choose the mixture of CPU bound and IO bound, because if we have more CPU bound, so most of the times it would be in the running queue. But if we have more IO bound processes, they would spend more of the time in waiting queue. So CPU would be idle. Here CPU would have more load and here it would be idle. So we should choose it wisely. Actually, schedulers should choose it wisely. And now we have the what are the operations that could be performed on the processes. The first one is creation. The process could be created. It could be created the booting time, and a user can create a process or a process can create a process. For example, we have the fork. Fork is when a parent creates its child process. It will give call to its own another process. Then we have the scheduling or dispatching. Scheduling means shifting from one process to another. So we are giving the CPU according to the priority. For example, we are running this task. Meanwhile, a task of higher priority is in the queue. So it's a duty to give the CPU to this task first. And all the smaller tasks must try to be completed before the longer time task. Then we have the blocking. Blocking is simply refers to the waiting state when any of the device needs the input output device or resource. Then we have the preemption. Preemption, for example, is again if one process could be switched to another process. So if not terminated, for example, we are executing P1 and this is the time limit of the P1 and it's not yet executed completely. So it's a duty to provide the CPU to this task P2, which have the higher priority. And then we have the termination. Termination could be successful like after it's completely executed. So it's also called the termination process, and we can use the command of exit. And then we have the operating system terminates. It's it's a due. It could be in the following cases: if it's fully executed, then the program would be terminated, or if the operating system terminates it, so due to the service error. Or thirdly, there could be a hardware problem. And fourthly, if one process is terminated by the other process, so then we have the termination operation on the process. And then, for example, if the parent terminates the child, why it would terminate? Either the time is exceeded, or we can free the memory, or if the kill command, kill system call is called, then also the parent can terminate the child. So there are two scenarios. One is if parent terminates but the child is still running, so that sort of child is known as orphans, and the booting process would take charge of these orphans and will do the work and kill them. Secondly, if child want to get terminates but the parent is not allowing it to terminate, so those child are known as zombies, and this would also be taken in charge by the initialization or init process of the booting process, and these would be killed. So these are types of the operations on the processes.